When we speak about potential energy, we always have to identify of what, where, and due to what interaction. So on the left-hand side of this equation, we have electric potential energy of a particle placed at a particular location R. Q is charge of the particle. V of R is potential at location of the particle. Potential, however, is not created by the particle, but it is created by whatever interacts with that particle. In general, actually, whenever we have potential and potential energy, because electrostatic interaction is not the only interaction for which we have a concept of potential energy and potential. For gravity, we can have the same thing, it would always, I mean, this type of relationship between potential energy and potential due to a particular interaction would relate certain attribute of a particle with the properties of the field. So, for example, if we were talking about gravity, we could have a very similar relationship. Gravitational potential energy of a particle at particular location would be corresponding attribute responsible for the gravitational interaction. So rather than charge, we would have mass, and instead of electric potential at the location of the particle, we would have gravitational potential at the location of the particle. All right. I introduced yesterday a concept of potential, and we just reviewed the definition. Let's now take a look what kind, and I remind you that potential, similarly to potential electric field vector, describe space. What happens in particular location in space? So, how about if we take a look now at the field, which we already know how to describe using electric field vector, and now describe it in terms of electric potential. I want to talk now about potential in the electric field of a charged particle. So let's say that we have charged particle, charge of that particle is Q. Now, this is not the particle of which we calculate potential energy. This particle is the source. As I'm interested now in the field produced by a particle. Potential energy, I can have potential energy if I place another particle in the field of this one. Well, let's recall how we because we already know how to describe using using electric field vector, and let's say that I'm interested in potential at point B, which is whose position is described by vector R. So from the definition of, not from the definition, from the relationship between electric field vector and electric potential, let me remind you that differential change in potential was opposite to the scalar product of electric field vector and displacement along a particular path. So if I want to find out potential difference between two arbitrary points like point A and B, I would have to integrate, because the separation between points A and B don't have to be differential. In principle, I started with that V at point B, or potential at point B minus potential at point A is opposite to the integral along a certain path, and it doesn't matter what path, because this integral, look that if I multiply electric field vector by a charge of a certain particle which moves from one location to another location, I will really calculate work electrostatic work performed by this particle on another particle. Now, electric interaction is conservative, and for conservative interaction, work depends only on the initial and the final location. It does not depend on this along which path an object moves. So because of that, we could also conclude that this line integral is independent of path from point A to point B. Well, I haven't selected point A yet, so how about if I choose it over there? But later on, we'll try to find out such a location for point A so that the formula for potential is the simplest. All right, so now I have just to choose a path. I marked a path. It doesn't have to be this one. It could be any other path, as long as it connects point A and point B. I'm choosing point A as the reference for potential. And let's now concentrate on the scalar product. So I marked here a segment vector along the path. Now, you remember how we assign segment vector? Do you remember that? How segment vector is assigned to a segment? It is assigned in such a way that its direction is consistent with the orientation of the segment, and the magnitude of the segment vector is equal to the length of the segment. So don't confuse segment with segment vector. Segment is a fragment of the path. Segment vector, which looks similar, but it's not the same because it's a vector. Segment vector is a vector. Segment is a part of a path. All right, so I mark here vector, segment vector. Now, electric field at this location is radial. Yeah, we know what is the expression for electric field vector. Coulomb's law says what is the electric field vector at this location. Now I have to evaluate scalar product of those two vectors, and actually I need explicitly to relate position with the value of electric field vector in order to calculate this scalar product. I have to make sure that I pick one variable of integration. All right, now from Coulomb's law, I mean, let's say that this point is at location r prime, so consistently from Coulomb's law, electric field vector has a value. Coulomb's constant multiplied by charge of the source of the field divided by square of the distance from the source to the considered point, and the direction of the field is radial. So this is a unit vector pointing from the particle toward the point at which I calculate the scalar product. And I have obviously to calculate this scalar product for all points along the path. But calculus takes care of it if I wrote it that way. All right, so now Coulomb's constant is a constant in this integration. Q is the charge of the source, so it also does not depend on the segment. Well, this quantity depends, and this quantity also depends. And the angle between these two vectors also changes, because where is the angle? It's over here. And so I can, how about if I mark it? So rather than having now written as the scalar product, I can write down that it's magnitude of the first vector, and it's a unit vector, so its magnitude is 1. Magnitude of the second vector, and magnitude of the second vector, let me remind you that since it is a segment vector, so it is equal to the length of that piece times cosine of the angle between these two vectors. Now take a look what will happen actually if I could do various things, but the one which I want really to do is to project, if I multiply this length by cosine of this angle, I will get projection of the segment vector on the radial direction. So on the in this direction. Can you see that? I will get that projection. So cosine theta ds really is by an increase in distance from the particle. So I wrote it that dr is an increase in distance from the particle, rather than having length of the length of that segment multiplied by cosine of theta. I can write down that that this product is equal to the increase in the distance or the difference between the distance of this point and that point. Yeah, precisely it is going to be here. Well, right now, so, what I achieved is that I expressed I expressed the scalar product in terms of one variable of integration, r prime, which is the distance from the source. You don't confuse actually this r with this r. Or even if I had an arrow over there. This is distance. So here I integrate with respect to distance. Direction doesn't matter. Well, it's an inverse, it's 1 over x squared in the tables. So using fundamental theorem of calculus, I can calculate this integral and find out that potential at point B is equal to Coulomb's constant times charge of the particle producing the field, and I have difference in the distances from that particle. That is 1 over r is inverse of the distance of point B from the particle producing field, and RA is the distance of my reference point to the particle producing the field. Just to make sure that you understand each other, why don't you, for a moment, just ask your neighbor if you don't understand a particular step somewhere, although it is just simple calculus. So it's, physics really ended here. If you have some doubts, you may consult with your neighbor. Go ahead. So for a minute, talk about it. Yes, Robert? It's, well, yeah, I got the question, what happened with that minus sign? Now, remember how we integrate power function. So if I integrate x to the n, the indefinite integral is going to be x to the n plus 1 divided by n plus 1. Now, this is, over here we have 1 over x squared. So that is x to minus 2. So if we use the formula how we calculate indefinite integral of this function, we will get that it is x divided by minus 1. So this is how that minus disappeared here in the indefinite integral. All right. Other, I mean, do you want still to talk about it, or is everything clear and we can go ahead? All right, let's go ahead then. Now, if we choose the reference point in a smart way, and we are going to do that, we will simplify the formula. We can make this formula simpler than this one by choosing appropriately reference point where the electric I mean by choosing appropriate that point A. Where would you suggest to choose point A? Shout it. At infinity, far, far away from the charged particle. And why did you do that? Because in this situation, 1 over RA becomes 0. And indeed, this is what we are going to do. So we derived an expression for electric potential due to a particle or point charge, and we got that electric potential at a certain location R due to a particle has a value equal to Coulomb's constant, charge of the particle producing the field, divided by the distance of the point of interest to this particle. Now you have recognized where is the reference for this potential. Reference for this potential is at infinity. Now, it is true that when we observe motion of charged objects in electric field, in most cases it is these are particles. In principle, forces are exerted on the object as well, but they have more academic value than practical. Whenever we try to control objects using electric field, these will be usually beams of ions or beams of electrons. An example of it is a cathode ray tube, which was commonly used in old TV screens with those big tubes, because now we are switching to different technology. So soon they will be obsolete, and probably your children won't even see them anymore. However, cathode ray tubes still will be used for some other purposes. So I think that we will have to learn about them for another 50 years at least. But the sources producing the field could be quite complicated objects. So let's now, here I forgot to say about this, because I mean, if we analyze this formula over here, we can recognize how if I want to write equipotential surfaces. Where are equipotential surfaces? Well, we see that potential depends only on the distance from the source, from the particle producing the field, which means that they will be concentric spheres. And so concentric spheres now form equipotential surfaces around particles producing, or point charges producing the field. And we have already discussed that the fields are radial. So I marked on this drawing, actually I marked both geometrical representations of the field, electric field lines and equipotential surfaces. All right, let's now go back to the what kind of electric potential is produced at a particular location if we have an extended object containing a lot of charged particles. Well, the same way like for electric field vector, well, rather than thinking about what kind of potential is produced by individual particle and adding potentials for individual particles, we will divide the object into differential pieces Now let's say I want to find out potential at this location due to entire object. So I have to divide object into small pieces. And each piece can be treated now like a particle, although it contains, in fact, a lot of charged particles. So I know what is the, I mean, from that formula which we just saw a moment ago, I can determine what is the value of electric potential at this location due to this piece, and I can repeat it for all differential fragments of that object, and by adding them, I will get potential at this location due to the entire object. Actually, fact that we can add them comes from the properties of work. Because think what will happen if two objects perform work on a particle. How to find out the net work? What do we do with it? We are adding them. Yes, so here, this is why we are adding potentials if we want to find out potential due to an extended body. All right, so contribution from the differential fragment is Coulomb's constant times charge of that fragment and divided by the distance from the fragment to the point of interest, point where we calculate electric potential. And in order to find electric potential at this location due to this entire body, I will have to add contributions from all differential fragments of the body. I also can recognize that Coulomb's constant is a constant, so we can take it in front of the integration. R obviously is variable. Sometimes it can happen that it isn't, and let's say if we, how about if we try to solve the problem for which we determined electric field vector at a particular location. As I have a linear object like this. It has linear charge density lambda, and I want it is a part of a circle, and I want to find electric potential at this location due to this entire body. How would I do that? So I will have to divide the object into small pieces. So if I consider now one piece, electric potential resulting from that piece is going to be Coulomb's constant times charge of this piece, and if linear charge density is lambda, so I will have linear charge density times dl, and then I have to divide by the distance from the fragment to the point of interest. So in this situation, it is going to be the radius of that arc. And if I want now to find potential due to entire body, I have to integrate it over the body. Okay. Well, I'm talking about the problem which we discussed for electric field vector, so I did not mention here again, but this was a constant. So the solution is for constant or uniformly charged object. So now I can have Coulomb's constant in front. Linear charge density is constant. It's independent of the piece, because if it is uniformly charged. Now, how about the distance from the piece to the point of interest? It happens over here that for all pieces we have the same distance, because I picked a particular point in space. So I can take out in front also that distance. And then I have to add over the object lengths of all those segments. It is even not worth using fundamental theorem of calculus now. It's better to find this integral directly from the definition. What am I going to get if I add lengths of all segments? The length of this arc, correct? So this integral is just length of the arc. Now I can recognize that if I multiply linear charge density for a uniformly charged object by the length, what am I going to get? Actually, I see that it didn't even matter that it was uniformly charged. Let's say that it isn't. Yeah. Think what will happen if it were not. If it were not, I wouldn't be able to pull out lambda, right? Do you see that? So I will have it over here, but over there I would have lambda dl. And if I integrate lambda dl over this entire object, what would I get? Think what is lambda dl. From the definition of linear charge density, it's the charge of the segment, right? So this is really dq. If I add now those differential charges over the entire object, what am I going to get? Q, which is what? Charge of this entire arc. Right, so no matter if it is uniform or not, I would always get that electric potential at this point is Coulomb's constant times charge of the object multiply by r. However, this time r is what? It's radius of the arc. And, well, it reminds me something that I know that we often try to use symbols which resemble, which indicate somehow the name of a considered quantity. So very often you write that r is radius. It's rarely radius. Here, in this solution, it happens to be the radius of the arc. But if we take a look at that formula which we just derived, what is r over here? Distance, correct. It's not radius. So remember that not always r means radius. Okay. How about if I show you a certain demonstration of electric field. Really, this lamp resembles electric field produced by a charged particle. Probably some of you saw them in shops. So if I turn it on, it will be. I wonder how it is going to look when we completely turn off the lights. All right. Now, can you see those blue lines which are almost radial from that sphere? Why they are radial? Actually, how about if I say something about the construction of this lamp? This lamp contains gas, which when it is hit by electrons, it glows. So, and electrons travel actually through this in these arcs. I mean, between the center and the glass sphere, there are electrons traveling. And when they collide with the gas, they make the gas to glow. And we see the glow of the gas. So gas is just to trace the paths of the electrons. And, well, you can recognize that those paths are almost radial. Why they are almost radial? Because, well, yes, because they try to follow, it's not exactly, but they try to follow electric field lines, because if an electron finds itself on, let's say at rest, at this point, let's say that line is like that. Line is horizontal. Consider a horizontal line. If electron starts with a small velocity at this point, well, it is going to accelerate. It always accelerates along a line, along the electric field line, because practically electrostatic force is the strongest one. So if we ignore all other forces exerted on electrons, then the force is going to be tangent to the line. And if line is straight, it will be just along the line. And if and in this situation, all the time acceleration will be along this horizontal line. So electron will travel in this direction, and the trace will make a straight horizontal line. Well, we see some kind of fluctuations of it, and it results from the fact that those electrons do not travel. They are also subjected to other interactions than the electrostatic force. There is also drag forces due to this gas, and actually, in a moment, I'm going to destroy the symmetry of the field, because right now it's radial, and we can see that from the symmetry, because it looks like two plates. One is that sphere. Well, both are spheres. Those two spheres produce the field. So from symmetry, we could conclude that the fields are radial. But if I touch that external one, now I ruined it. I ruined the symmetry. And indeed, my finger now makes the potential at this point to be ground. The same as mine. So now electric field between that inner sphere and my finger is much stronger than in any other direction. And actually, you can see that arc, bends upward. Then it breaks when the line becomes too long. So the field along the electrons, it's too hard for the electrons to travel that far, so that arc stops, and then a new one starts from a horizontal. Now, the fact that it goes up is caused by convection, because the arc hits that gas over here on this side of that sphere, and it drags the arc upward. I wonder what will happen if I make two. So it alternates one way or the other. All right. Now I would like to actually, because so far we are talking about the fields in the absence of matter. But if we place substance into electric field, it is going to be affected. And let's start. The reason for the changes is because molecules of the substance will align themselves in particular way to affect the field. So in order to understand this, I will start with a discussion of an object which contains two charged particles. If we have, it's something quite common in nature. Yeah, it's we can have chemicals, molecules will behave in such a way in electric field. So if we have two oppositely charged particles and they are bound, so they stick to each other, this object is referred to as a dipole. Let's see how a dipole, well, let's start with this. What is the charge of a dipole? The total charge of Robert says that it's 0. And indeed, it is 0. Charge of the dipole is 0. Now, dipole is relatively small. So if we place dipole in an electric field, for simplicity, think about that we place it in a uniform electric field. Well, no matter what, can we actually use the expression that the force exerted on the dipole is going to be 0 times E? Yeah, because according to the definition of electric field vector, force exerted on a particle is equal to charge of the particle times electric field vector. Can we use this formula for a dipole? Christie says no. And why not? Christie is right. Because this formula, the definition of electric field vector, requires, what is Q in that formula? A what? Charge. Yeah, what charge? No, it isn't charge of the dipole. It is charge of a particle. Correct. Dipole contains two particles. However, if I take a uniform electric field, well, then I can recognize that force exerted on this particle is going to be opposite to this one. So in a uniform electric field, indeed, the force exerted on the dipole is going to be 0. Is dipole going to accelerate in any way? Can you imagine it? How? To the left, to the right? In a circle, correct. So actually you are saying that as the object, it is not going to accelerate. Center of mass of the dipole would not accelerate. However, the dipole will turn orientation. A torque would be exerted on the dipole even if the resultant force is 0. Let's estimate that torque. And actually, if the total force exerted due to certain interaction of a system of particles is 0, then it doesn't matter about which point we calculate the torque. Torque about the center of mass, let's say that these two particles have the same mass, or torque about this point or that point will always have the same value. Check it. So for simplicity, I calculated torque about this point. And why did I do that? Because if I calculate torque about this point, torque due to force exerted on this particle automatically is going to be 0, right? Because the lever arm is 0. Now, instead of, I mark a vector from the negatively charged particle to the positively charged particle. So this vector is a vector which has direction along from negatively charged particle to positively charged particle, and its magnitude is equal to the distance between the particles. So it's almost like the segment vector. So from the definition of torque, the total torque exerted on this dipole will be 0 plus vector product of vector d and force exerted on that positively charged particle. Which product is that? Cross product. The result is going to be a vector, correct. Now, that electrostatic force is related to the electric field vector. It's charge of that red particle multiplied by electric field at that particle. If it is uniform, then it even doesn't matter where. Now, vector product has such a property that if I have a number, it does not matter where I put the number. So I will put the number next to D. And the reason that I did that is that now I separated contributions to the factors among the field and the particle, or the dipole. Q and D really characterize dipole. Do you see that? Q is the charge of the particles forming the dipole, and this vector is related to the separation between separation and orientation of the dipole. So here I have a product which characterizes the dipole, and here I have a quantity which characterizes space in which that dipole is. This product is referred as dipole moment. And for a dipole moment is equal to the charge or absolute value of the charge of each particle multiplied by a vector connecting negatively charged particle with the positively charged particle. And then consistently with this derivation, I can recognize that the torque exerted on a dipole is equal to dipole moment multiplied using vector product with the electric field vector at the location of the dipole. This formula is a formal definition of dipole moment of any object, because so far I discussed here only a dipole. But if I have any object, not necessarily dipole, it still can have a dipole moment. And if it has a dipole moment, then the electric torque will be related to electric field by this relationship. So we can recognize the dipole moment is in the direction from negatively charged particle to positively charged particle. And at the end, how about if I show the demonstration what happens with particles which have dipole moments. So far we discussed a dipole. But this molecule, some of you, particularly those who study chemistry, could recognize. Anybody recognizes this molecule? This is water molecule. Water molecule is not a dipole because it contains 3 particles. However, it still has a dipole moment. Now in this simulation, I will be turning on electric field upwards. So how about if we start, I think that they are not moving initially. Right, they are not moving initially, and the particles are not moving initially. And now I will increase the field upwards. So we can recognize that now those particles try to align themselves in such a way that the positively charged particles move upward, negatively charged particles move downward. Actually, this simulation is so good that even shows interactions between those 2 particles. They attract each other. Dipoles can attract each other. All right, so this will be all for today, and we will continue tomorrow.